Okay, welcome everybody to today's INQA seminar. It's the 1st of July 2025, and this is the last ever online INQA seminar. We've had 3 years of fantastic seminars. Thanks to everyone who's given a seminar, chaired a seminar, attended, asked questions, and a reminder that all the seminars you can find on the INQA YouTube channel. So, without further ado, I shall introduce our final grand finale speaker. So, today's presentation is given by Mohammad Amin, who is I may get the title wrong, Chief Scientific Officer. Is that correct?
No, chief
Mohammed
scientist.
from Chief
Chief
Scientist, I do
scientist.
apologize. Chief Scientist of D-Wave. And Mohammed has certainly been one of the leading figures in quantum annealing over the last quarter of a century, I'm going to say. Fantastic. So without further ado, I'll hand over to Mohammed, who can talk about quantum annealing beyond optimization.
Thank you, Paul. It's an honor to give the finale of this wonderful seminar series, although I'm sad to be the last to ending this series. So Paul asked me to give an overview of quantum annealing over the last 3 years of INQA. I searched the archive, and there have been more than 1,000 papers over the last 3 years, which is a fantastic thing for this field. But I don't feel qualified to to give a comprehensive overview of 1,000 papers. I certainly don't know a lot about a lot of them, but I'm qualified to tell you what has been going on and what's the biggest change within D-Wave and within D-Wave annealing processors that allowed to do a lot more than optimization, and that's the title of my talk, the quantum annealing beyond optimization. So for those who have been in this field long enough, as Paul said, back in the early 2000s, when the quantum annealing and adiabatic quantum computation were introduced, people basically mostly use adiabatic quantum computation, and the term quantum annealing was rarely used, except a few papers. And people kind of took these as synonymous, like the same thing. Quantum annealing is adiabatic quantum computation. Adiabatic quantum computation is exact optimization. The goal is to find the grounded state of a Hamiltonian and evolve adiabatically. The bottleneck is the minimum gap, and how the minimum gap is scaled. That was the type of the questions asked back then. But over these years, people realized that this is not true. Quantum annealing is not adiabatic quantum computation, except if you anneal very, very, very slowly and if everything is coherent. And adiabatic quantum computation is not the best way of optimization. And indeed, what we do at D-Wave is far away from adiabatic quantum computation in terms of the speed of evolution and in terms of the environment. So I would not call quantum annealing adiabatic quantum computation anymore at all. And the goal is not exact optimization. Indeed, with quantum annealing, you can do a lot more. You can do approximate optimization, which is still one of the most important applications of quantum annealing. But you can do more. You can do quantum simulation. You can do AI. You can do, recently we showed blockchain. And those who were in AQC conference, Rahul presented a new application, digital analog quantum computation, which will be available soon. So I'm not going to talk about optimization, because that's where majority of 1,000 papers are. I'm going to talk about the rest. And just before that, I want to mention that many of these applications were enabled by advanced controls of quantum processors, whether fast anneal and other controls that are available or will be available. Okay, let me start with quantum simulation. But before that, I want to just very briefly say what is quantum annealing and what D-Wave does. This is the only formula I present in this paper. It is a very non-technical presentation. And I'm lucky that this is a quantum annealing community, so I don't need to talk too much about even this formula. So this is basically the Hamiltonian that our quantum annealing processor provides, a transverse term and a longitudinal term with two coefficients, A of S, B of S, that change with time like this. Blue is A and green is B, and horizontal axis is time. And here I have to acknowledge Rahul, who made this figure, beautiful figure. I just copied and pasted. And Rahul also puts physical temperature here to have a comparison in terms of energy with these coefficients. The temperature is pretty low, but nevertheless, because the annealing, if you have slow annealing, temperature will have significant effect in the result. But if you can do fast annealing, I mean in nanoseconds, less than 50 nanoseconds, then basically your machine solves Schrödinger equation. And that would be quantum simulation, basically simulation of any problem that requires solving a Schrödinger equation. We published a few papers. This is one of the major one. We published in 23, and this paper is simulation of critical dynamics of a spin glass going through a spin glass phase transition. 5,000 qubits were involved, and we saw very nice agreement between theory and experiment. The symbols here are D-wave results, and the solid line is what you expect from theory. And up to 50 nanoseconds or more or less, the system follows what you expect from a Schrödinger equation. And even more importantly, this shows this figure, which is a key figure in the paper, shows that the residual energy converges toward lower energies or towards zero faster, better scaling that classical algorithms. And this is the theoretical and experimentally proven, or one of the main and only theoretically and experimentally proven of quantum advantage in optimization, both in quantum annealing and gate model. But more than that, earlier this year, we actually published a paper in Science trying to simulate quantum Schrödinger equation dynamics, Schrödinger dynamics behind this data. And it turned out that it is extremely difficult. And what this machine did in minutes, you need to run frontier supercomputer for 1 million years to reproduce the same result with the same quality. So spin glasses are not the only, and I want to just mention that this is the first and the only still demonstration of supremacy in a real world problem. And if any other demonstration were on random number generation, those that survive. So spin glasses are not the only system that you can simulate. I'm pretty sure if you think hard enough, you can find many more problems that you can solve with this machine. This is one example that was published earlier this year on the archive by D-Wave and Los Alamos National Lab and UBC. And this is a simulation of magnetic material simulation of high-zinc fluorines. I encourage you to think about other examples and try to do this kind of simulations, because you may find results that can never be obtained by any classical computer. And that's my actually ideal, that to show some physics that classical computers can never simulate. Okay, so now then the next topic is artificial intelligence. And nowadays, generative AI is fashionable with GPT and many other now platforms. So this is one way that you can actually use quantum annealing in AI. That's in variational autoencoders. So for those who don't know what variational autoencoder is, basically you have a set of data sets, which are images. Those who know my dog, this is my dog Milo, who I usually bring to the office. So you start from the images, and you train an encoder and decoder in such a way that you turn this image from pixel environment to a latent environment. And latent now, for our case, is binary numbers. So you turn pixels into a binary bit string, and then you train a decoder to turn it back into the same image. Of course, you cannot turn it back 100%, but it will be pretty similar to the original image. And once you train it, then basically your encoder decoder can actually determine a latent representation or binary representation of your data. And if you train a prior, by prior means some distribution, in our case is D-Wave quantum computer, then the prior or D-Wave can generate the bit strings required to generate images. And if you do your job well, you hope that in the sampling phase or in the generation phase, you remove the decoder and then just you take sample from your QPU and turn it by the decoder into an image, and you hope that you can generate an image that you have never seen before. And that's what generative AI does. So this is this proposal that using D-Wave QPU or quantum annealer or maybe quantum boson machine in general goes back to 2019. We wrote this paper in Quantum Science and Technology, and some years later we actually did the first experimental demonstration of that, very small demo that this can work. But recently Triumph Group, which actually we started collaborating with them with Wojtek back then, and then they continued, we didn't. And they succeeded to actually use this framework to work with high energy physics. And with the current complex QPUs that we have, we see very nice results. I will let you read these papers and judge by yourself. This is a more recent one that was published last year. But you also have, you can also use it in other areas, not just high energy physics. This is a very recent news that Japan Tobacco released about using large language models like GPTs, like transformer models, for drug discovery within the same autoencoder, variation autoencoder framework. And you can also use the same idea in other models, like diffusion models that are used for generation of images and videos. This is a paper by two of our former colleagues that are now at the NVIDIA, and they trained a diffusion model with some latent variables. They did not use D-wave, but you can easily replace the discrete latent variables with binary numbers and use D-wave to sample the way they did. Okay, so now I want to go to the next topic, and that's blockchain. I'm going to spend much more time in blockchain because I know a lot of you don't know what blockchain is. If I don't have time, I will not spend much time on the last topic because we don't have the hardware available on the leap. So what's blockchain? So imagine two people, I call Alice and Bob because that's the normal name people use. So imagine two people want to do transaction and they don't trust each other. They don't trust each other at all. But nevertheless, they want to do transaction. How do they do that? So traditionally, you invite an authority, and the authority witnesses the transaction and documents the transaction. And in that document, then it says what happened, and any conflict later, you go back to that document as the reference, and the authority as also as the reference. This is actually a very old way of doing transactions. It's 5,000-year-old practice. If you don't know, writing was invented exactly for this by Sumerians, to record transactions. Writing was not invented to record kings' adventures and history, but to record transactions. So I'm showing two of the oldest Sumerian tablets. The left one is a single transaction, and the right one is a block of transactions. Now you know what block means. It's a block of transactions, many transactions, written on a clay tablet. And if back then they could chain those block of transactions, they would have invented the first blockchain, but they didn't. We needed another 5,000 years to invent blockchain. So now, imagine you want to do transaction without the authority. How would you do this? So again, another old-fashioned way was to bring witnesses. So a lot of witnesses, the more the better. Maybe the whole village, or maybe all the families of the two persons in the old days. And if there was a conflict after, then you bring your witnesses, I bring my witnesses, and then the one who has more witnesses wins. And so in this case, if you choose large number of witnesses as the witness, cheating requires convincing more than half of the witnesses, validators. If you want to bribe them, it may cost you more than the transaction that you're talking about. So then cheating becomes impossible unless you're a king or something. But how can you do this now? You cannot bring thousands of people to witness every transaction, but you can do it by thousands of computer nodes. And that's what blockchain does. So you basically have thousands or tens of thousands of computer nodes witnessing all transactions and recording all transactions and keep the record everywhere. And that's what's called distributed ledger, that every transaction is recorded and added to something we call blockchain. And then every computer keeps the record. So therefore, no one can cheat. There's a consensus mechanism, which is basically the majority vote. There's a mechanism in such a way that if you want to cheat, you have to control more than half of the computers. And that will be very expensive to add enough computer to be able to cheat. So that the expense will be more than the reward of cheating. Okay, So now what is blockchain now? So again, I told you what block is. Block is just a list of transactions with some other information which is not important right now. And you basically chain them. Connect them by a chain. What the chain means here is a cryptographic hash. Okay, so I know some of you may not know what hash is. A hash is a function that converts an arbitrary length input into fixed length output. So probably the simplest hash that you all know and you don't know you know is just postal code. You, no matter how long the postal address is or how short it is, you turn it into a fixed number of characters. Like in Canada, it's 6 characters. And that's basically a hash. And the nice thing about postal code is invertible. So if once you know the postal code, you can actually turn it back into exact address or approximate address. So it's a two-way conversion. But that is not cryptographic hash. Cryptographic hash is one-way conversion. So you can go very easily one way, but you cannot go the other way, hopefully at all. So how does the hash help? So now imagine every block depends on the hash of the previous block. And you hash again, and then hash again, and hash again. And any change in any of the blocks will change the hash of all the blocks after, because they're linked to each other. So therefore, once a block is added, nobody can change anything without everybody noticing that everything is changed. So no information can be changed or removed when a block is added to the blockchain, and the blockchain is distributed among thousands of computers. Therefore, it's basically completely secure. So now, how to make thousands of computers participate? And that was the ingenious ingenuity of Bitcoin that actually started this. So how to do this? You introduce a competition with a big reward. So the reward is now very big, but back then it was just a reward. And motivate people to compete, to win the reward. Nobody cares about blockchain, nobody cares about transactions. They want to win the reward. But everybody, in order to win the reward, should validate the transactions. And the reward should be somehow that everybody has equal chance of winning. And the reward should be large enough that it is worth for me to buy a computer or many computers and try to win this reward. And that it's called mining. But however, the total cost of computation over the whole network should be so large that if I want to do some fraud transaction, I have to buy as many computers as all of the computers to win this consensus or majority rule, and that's impossible. That's prohibitive. So therefore, basically, you have a secure way of validating transactions with thousands of computers participating in validation. So how does it work in practice for Bitcoin? The competition is solve a puzzle, and in this case it's cryptographic puzzle, like finding a hash that has X number of zeros, and there's no other way than trial and error, because hash is not invertible. So because it is just trial and error, it's equal chance of anybody to win. Find the hash and win. And another important characteristic is this puzzle is very challenging, but once you find, it's very easy to verify because it is basically a hash with X number of zeros. You can just look at the hash and see it's a lot of zeros. The reward in Bitcoin is in cryptocurrency, and the cost of cheating is so large because there's so many miners in the world that you can basically never ever win 50% of the vote. But the difficulty of the drawback is it sucks a lot of energy of the world. It is currently the cryptocurrency is like 200 terawatt hour per year, which is more than some of the electricity cost of some of the countries, consumption of some countries. So that's a problem, and it can become bigger and bigger if this is a way of doing transactions. If you want to have this is a way of transactions, it will be very, very costly in terms of environment and energy, and it's just waste, basically just wasting energy. So the solution we found was if you replace the puzzle with a quantum supremacy puzzle, then you really need a quantum computer to solve the puzzle. And the energy consumption of quantum computers are very low. Therefore, if that becomes like in the future, in some years, become a thing, then it saves the environment a lot of waste of energy. So this was the main idea. We had this in this paper, blockchain paper. We used our supremacy results. So the challenge we had was the quantum mechanics is probabilistic, but hashing should be deterministic. And we basically solved this problem, how to incorporate this probabilistic into the blockchain. And we experimentally tested the blockchain using 4 quantum computers located in different places in Canada and the United States. And it worked. And this is how this blockchain evolved. So you start from one block, you add a block, and at some point there could be 2 blocks added together. So whether just randomly or whether because of probabilistic nature of our hash, and both of them grow. But there is something called the longest chain rule in blockchain, that the chain that grows faster will be dominant and this one will be ignored. So it's basically a self-correcting mechanism that is commonly used, and we modified it a little bit to take into account the probabilistic nature of quantum mechanics. And this is how the blockchain evolved. And this is an animation that Jack generated. It's a real world blocks added to blockchain using 4 quantum computers. And the blue ones are the ones that are accepted in the blockchain, and the orange one is basically a chain. You can see the chain, that part of that branch ends when it is green, orange. And the block are the new blocks that their fate has to be determined. Okay, so I think I can spend like a couple of minutes on talking about analog digital. Okay, sure. Okay, so this is a new technique.
One question, Mohammed. Can I ask a question?
Yeah.
So what if when someone makes a better, more efficient, more faster annealer than you have?
Okay. What do you mean? For blockchain?
Well,
Yeah, it's a competition. If anybody makes a better annealing, and actually, I think if you really want this to win, it should be a multi-platform, like something that even gate model can contribute, and people try to. It's not like a one company idea. It's something that if you can come up with
Probably,
something that many different platforms works even better, because that kind of blockchain will actually
but
win
it's
all.
still
Yeah, go ahead.
it's still based on a spin glass problem.
Yeah, but it doesn't have to. So in the paper we have many other proposals that we just use that because that we showed that there's supremacy demonstration for that spin glass problem. But the idea is just find a puzzle that you can reproducibly, independently by different computers solve and validate each other. That's a very important point. So if
But what if someone comes up with like you have some spin glass based problem and someone comes up with a classical algorithm that does just as well for that
if
problem?
then that person can also win, but it also has to be able to be as fast as our quantum computer. So like if somebody can find a classical algorithm that can solve quantum phase transition in 5,000 qubits, yeah, they deserve to win the prizes. Yeah. Actually, this is another interesting thing about this blockchain. It encourages people to think about ways of actually solving this puzzle. And if this puzzle is an interesting problem, you're actually creating the people using people's intelligence and do something useful than just doing wasting energy.
So in effect, you're coming up with, let's say, more creative one-way functions that, in some way.
Yes, yeah, yeah. But the agreement between different quantum computers is very important. That's the challenge. So like for example, this random circuit model that is fine-tuned to the random circuit sampling is fine-tuned to one hardware and another hardware cannot reproduce is not useful. So you need to be able to multi-processors solve exactly the same problem and agree with each other and validate each other. And that was a challenge, and that's the beauty of this. Having 4 processors validating each other is non-trivial, but it worked. Okay, so the final is the new possibilities that actually one of our colleagues, Rahul, came up with, which actually within the quantum annealing architecture, and we can do some unitary operators, single qubit unitary operators, equivalent. We don't do gates. We basically do some evolutions, but which are equivalent to unitary operators before and after, like the analog part of our evolution. And this is kind of a limited version of digital analog, because only before and after, and they cannot repeat it. It's just, but nevertheless, it can introduce a lot of flexibility in many things, including like a hash. You can define a blockchain, a hash this way, and I would actually do it in such a way that people can compete. Like gate model can also compete and generate this hash. And if they can generate thousands of qubits with the same accuracy, then they can also compete. And that would be an interesting competition. Just to show you results, this is a 2-qubit result. This oscillation means that you have 2 qubits. You basically excite one of the qubits and then doing this kind of initialization, and then you see that the state oscillates between the 2 qubits, qubit 1, qubit 2, There's an oscillation happening. But more interesting is this plot that Rahul generated. It's a 64 qubit ring around our processor, and on top left you excite one of the qubits, and on bottom right you see that this as time evolves, this excitation propagates to the other end and goes back. This is a multiple measurements Rahul did. So these are possibilities that will be available soon. For conclusion, I want to say that with advanced controls, especially fast annealing, that we now are available and will be available, we can do many other applications beyond optimization. And I want to encourage people to think about these applications as well as optimization. And those could be this quantum simulation, generative AI, blockchain, and hopefully many more people will come up with. And yeah, and as I advertised, digital analog will also become soon. Even I think with Advantage too, we have some plan, but the next generation we will actually design some hardware special for this kind of capabilities, which makes readout within annealing or at any point of annealing possible. Readout in any basis is possible. Initialization in any basis is possible, and we can do a lot more with quantum annealing. And with that, I want to thank you for your attention.
Excellent. Thank you very much for a very nice presentation there, Mohammad.
Thanks, Mohammad.
Some interesting ideas going beyond optimization. And I guess I'll now open it up for questions. So if you have a question for Mohammad, then either just unmute yourself and speak up, or turn your camera on, or put some in chat, or raise your hand, all the usual Zoom methods for attracting the chair's attention.
Well, if no one else, I can ask a question about this last thing. I mean, I guess there's a number of ways that you could do this, combining that is digital with analog. And I guess, I mean, if I'm correct, the way you guys have done it is it's sort of like in the old days when we did qubits, we weren't using microwave gates, we were using fast pulses to change the basis and stuff. So I think that's what you've done. But I guess a really straightforward thing is just to be able to do Rabi type manipulations on some of these qubits, and you could achieve similar things. Is that correct?
Yes, but Rabi requires microwaves, and microwave requires a large bandwidth lines. The nice thing is within the current bandwidth, so without introducing large bandwidth and more noise, and within the current bandwidth of our I/O lines, we could do this. That was the beauty of this. The main idea, I think if you heard Rahul, the main idea was to do this manipulation that you said, this pulses, instead of applying that pulse by a high bandwidth line that gives a pulse, we use other qubits. And because we can manipulate our other qubits to switch fast, quickly, even with a slow line, we can actually switch a qubit fast and then do the fast pulse to the other qubits. So that was the way it worked.
Yeah, I guess you're putting a really large amplitude pulse on a qubit and effectively getting something fast that way, a kind of workaround of the low bandwidth lines.
Exactly.
But I mean, I guess the problem is if you want to really make this more general, then you, I mean, the way I understand the processor now is that you've made a lot of simplifications to solve the wiring problem. So to get really independent annealing controls, you've got to you've got to get more wires in some ways, or some other ways. You've got to back off a little bit. But I think with microwaves, they're sort of everything can be rather frequency addressable, so that helps a little bit with the wiring. You can, if you can tune qubits around. But I think there's lots of solutions here. I think this is
Yeah.
really fascinating and probably a lot of possibilities.
Sure. Yeah. Yeah.
I think Dennis maybe has a question.
Yes, yeah, thank you very much. About the blockchain. So I'd like to know, I mean, the D-Wave QPU, as any quantum computer, is a probabilistic device in the sense that it generates a certain set of bit strings with some probabilities. And for a hash function, you would need a deterministic scheme, right? So how do you get around that? Like, maybe the question is rather, how is the problem defined in a way that you get like a deterministic output?
Okay, so you don't get this deterministic output. That's the point. But the thing is, the blockchain has a self error correction, that I told you. If you have because of probabilistic, two miners add blocks in parallel, one of them will be ignored and the other one will continue as soon as one of the chains become longer. It's the longest chain rule that I mentioned. So we made some modification but the problem is maybe half of the miners will be ignored. So we came up with some way that we incorporate this probabilistic into the validation rule in some way to actually reduce this inefficient mining. I would encourage you to read the paper. I don't have time to go to details. There are a lot of details involved, but yeah.
Yes, for sure. Yeah, no, I'll definitely do. And I guess then I'll also learn how the solution of the Schrödinger equation is connected to this, like the computation of the residual energy for a certain set of, for a sample set or something. So
Oh,
I
you
guess
mean?
that probably also goes too deep, right? To
Oh,
go.
that is. You mean this
I
original?
mean, I'm familiar with the 5,000 qubit paper by Andrew King and you guys.
Yeah.
But I'm wondering like how this physics problem is used in the blockchain.
Oh, the physics problem.
Yes.
We just basically defined a puzzle based on the solving Schrödinger equation. You
So
have
in the
to
way,
solve it within some accuracy, so
so
that
is it really then, is it really the residual energy that you
no, it's not residual energy. You have to basically find all the correlations correctly.
okay.
Yeah, and within some error, and once you reach that error, then you get others can validate that.
Okay, very good. Yeah, I think I have some idea now, so I'll definitely look at the paper. Thank you.
You're welcome.
So maybe I have a question. Going back to your variational autoencoder,
Yeah.
which I guess clearly works to some degree. So if I've understood correctly, the role of the D-wave is in the yellow box marked prior.
Exactly.
But what is it about a quantum computer, or specifically the quantum annealer, that might suggest it's good in some sense in this application? What are its properties that make it good here?
So so you want to turn your data into some binary strings, and generally the binary strings that represent data comes from very complex distribution. So then your goal is to have a model learn that distribution, know that distribution, or generate that complex distribution. And so the role of quantum computer is to be able to sample from a complex distribution pretty pretty quickly. You can use other samplers. You can use RBM, but our QPU can sample and learn quickly and better than RBM. So one of so for example, for this application of high energy physics, speed is very important, because there's in high energy physics, a lot of data are generated constantly in CERN, and they need to do constant simulation in different conditions to be able to analyze those data. So speed is a significant factor here.
So does the effectiveness of the D-wave as a fair sampler presuppose that it's somehow doing Boltzmann sampling, or is it more complicated than that?
In some frameworks,
there are some circumstances where it will not give you a Boltzmann distribution. This is
In some frameworks, like this one that this Triumph people use, you need to assume Boltzmann. They assume Boltzmann distribution.
Okay.
But in general, if you can train, it doesn't need to be Boltzmann distribution. If you have a way to train it without a Boltzmann assumption, that's something actually we are working on right now.
Okay.
It doesn't need to be Boltzmann. As long as it can represent the data correctly and quickly, that's good enough. So it doesn't need to be a Boltzmann distribution.
Interesting. Good. Any other questions for Mohammad? Well, I don't. There was a question appearing in the chat a moment ago, but it seems not to be there now. But I guess I don't see any questions. So let's thank Mohammad once again. Thank you very much, Mohammad. Nice presentation. Round of applause from me on behalf of everybody. And that brings to a resounding conclusion the last 3 years of INQA seminars. And just to remind you that from now on, INQA will transform itself into an annual conference, which next installation of which is taking place in Barcelona in November. So check your emails for information about that. But without further ado, thank you very much for everyone for attending, and I hope to see as many of you as possible in Barcelona in November. Bye-bye.